Let's examine some overlay operations. Overlay operations are going to involve combining spatial and attribute data from two or more spatial data layers. In other words, we're stacking the data and looking for places where the data overlap. While the overlay operations may seem simple when used alone, they can actually be pretty powerful operations when they're combined in series. An example of an overlay operation would be the clip operation. For example, let's say I have a data set that contains all the streets in the United States of America. However, I only want the streets in Arkansas. I can use the clip operation to cut out all the streets that are only in Arkansas by providing a state outline of Arkansas as the clipping feature. One thing to note about the overlay operations are that overlays require that the data be in the same coordinate system. This is so the software can perform the highest accuracy of overlay. Some software packages automatically reproject on the fly if the data is not in the same coordinate system, but this is really not the preferred method. The first type of overlay operation we should discuss in this section are vector overlays. A vector overlay involves combining point, lines, or polygon geometry and their associated attributes. All overlay operations create new geometry and a new output geospatial data set. You should be cautioned that with certain overlay operations, very large attribute tables may result if the overlay operations combine many layers and each layer has a very large attribute table. Additionally, it might be possible that the combined attribute tables would cause duplicate attribute fields to exist. In these cases, you really should consider reducing the number of transferred attributes to the minimum needed and then renaming any duplicates fields so there's no ambiguity. The first basic case of overlays is the clip function. The clip function defines the area for which features will be output based on a clipping polygon. I like to think of this in terms of cookie dough and a cookie cutter. The cookie dough is the data layer that we want to reduce in size based on our cookie cutter. The clipping layer is the cookie cutter that will determine how we cut out the part of the cookie dough we're interested in. It is important to note that in the clipping operation, the only geometry and attributes of the data layer that are transferred to the resulting layer. So only the geometry and attributes of the data layer are going to be transferred to the result layer. So neither the geometry or attribute of the clipping layer are included in the output, just as you would not make your cookies in the oven with the cookie cutter still surrounding the cookie dough. The next basic case of overlay is the intersection operation. The intersection operation combines data from two or more input layers, but the combination only exists for the regions where all the input layers contain data. This is similar to the clip function. However, the attributes and geometry of all input data layers are going to be transferred to the result layer. The third and final basic case of overlay is the union overlay operation. The union operation is an overlay that includes all data from all input layers. Since the union operation combines all the attributes and all the geometry, no geographic data are discarded in the union operation, and all of the corresponding attribute data are going to be saved for all regions. When performing vector overlays, there are a few problems that you should be aware of. In the case where the input features represent common features that are represented in both layers, they might have slightly different geometry. This is going to create something that we call sliver polygons, and this is when the overlay operations are performed. For instance, we can imagine we have one input data set that represents the national boundary of Canada, created at a 1 to 5 million scale. We have a second input data set of the national boundary of the United States of America, created at a 1 to 2 million scale. If we stack these two layers on top of each other, it's probable that the boundary lines will not overlay exactly as they were created at different scales. And therefore, the Canadian boundary line has probably been more simplified than the US boundary line. The area where the two input data sets do not match is going to result in a very small and typically insignificant sliver polygons, but we need to deal with these. There are several methods that exist to reduce the occurrences of slither polygons, such as manually snapping the boundaries together, or introducing fuzziness to the edges of the overlay operation, or simply manually deleting these sliver polygons. To illustrate the idea of a sliver polygon, here are two different data sets, one outlined in a bold black line and the other outlined in a thinner gray line. Where the two data sets overlay, they do not match up exactly for whatever reason. If we perform an intersect, clip, or union operation on these two input data sets, we are going to create 3 sliver polygons. The sliver polygons created between these two input data sets are going to be highlighted here in red. The sliver polygons are probably insignificant and are the result of data sets being produced by different agencies or created at different times and probably at different scales. And it's really up to you to determine how you would like to solve the sliver polygon problem.